to our presentation. So I hope everything is right. The issue with this thing is that I am not able to see what you are typing or what you are doing in your particular other window. Hopefully everything is fine, and if you have anything, uh, any issues, you just need to get back to me through your mics. You can switch on the mics or the videos, and then ideally the mics, which will help me to realize there is an issue. Okay. So otherwise, I will go back to my presentations. Just be aware of that. You need to somebody else to switch on the mics. Raisel, is it wanted or unwanted?
Sorry?
Have you switched on the mic? Do you
Yes,
have a
sir.
record? What is the issue?
There is no issue, sir. I can hear you.
Okay, then you can switch off the mics. Okay, so very small. One second. Okay, so coming back to what we are trying to deal with. So it's WCA Plus. It's called as enhanced worst case analysis. It basically tells you what are the worst case scenarios, or what is the probability of these scenarios being the probability of happening of this particular scenario, so that you can deal with that particular situations effectively. So it's the idea of your WCA Plus. We have already seen the basics of it. Now, these are the 10 steps which are associated with the performance of your WCA Plus. If you want to perform WCA Plus, you need to follow these 10 steps. So we will go through each of these steps in detail. It's quite implied steps. The first thing that is required to be done is your definition of analysis requirements. Then you need to establish derating factors, determine global parameters, uh, develop the design equations, identify the worst case solutions, determine the margins, calculate alert probabilities of occurrences. From this particular point, uh, calculate alert probabilities of occurrences. It comes as WCA plus. WCA is stops under the determination of the margins, and then just telling that these are the alert scenarios. Probability of it, the solution of it, how do you make this particular thing corrected? Do you optimize this? All these will come under your WCA plus. So this is a WCA plus steps which will be proceeded by calculation of alert probabilities of occurrence, then reconciliation and feedback, perform a risk assessment, correct and optimize the design. All these will come under the usual, what to say, WCA plus category, but we are not differentiating much about WCA and WCA plus. We are defining the steps which are ideally required to produce a document which can be effectively used to change your design, to understand the issues with the design, to understand the worst case scenarios, and if required, make the corresponding changes. If not required, you have this particular document, gives you an information regarding what is good and what is bad. Okay, so that's the idea that is there. So this is your full screen mode. Okay, so we will move on to each of these steps now. I mean, there is a theory associated with it. There is a practical scenario of identifying these things. There is appendix B and C in your textbook, where they have defined, or they have given a document with a WCA plus analysis, which gives you a good insight into how things are done. There are certain examples which are considered during the process, but I guess looking into your appendix C of this particular thing will give you a much better performance. I'm not going to complete whole steps. Ideally, I will stop with step 5 in today's class. We'll move to the step 6 to step 10 in the next class. And after that, you need to go through that particular document, understand the stuff, and come back with questions in the next session. That is how we are going to deal with this particular WCA plus analysis. Okay, it's quite interesting. It's quite interesting to understand what WCA plus is. Okay, so first is define the analysis requirements. Okay, you are starting an analysis, you need to understand the requirements of it. So that's, we have already seen the significance of requirements at different levels. So you are trying to do an analysis, you also need the requirements of the analysis. So you define the scope and depth of the analysis by design teams, company experts, outside consultants. Everybody has to tell that this is the jurisdiction of our analysis. This is where we are trying to analyze. This part is where we are trying to analysis. And then it is split up into different tables. It's bound to different cases. Analysis always has cases: case 1, case 2, case 3. Small analysis cases. The cases are defined by something called as analysis table. Okay, inside an analysis table, you'll have case 1, case 2, case 3. It's a typical way of representing an analysis kind of setup. Okay. And it is mainly used for, we have already seen that you have functional analysis, you have, what is it? You have your application analysis, and you also have the extremity analysis or the stress analysis. Okay, so this table is mainly intended for your functional analysis. Okay, functional stress analysis requires stress parameters. So functional analysis just speaks about the functional margins of the device, and then stress analysis considers the stress parameters. Application analysis addresses all the applications and miscellaneous supporting data. So you can have an analysis table which supports only your functional analysis, or you can have an expanded analysis table which has all these kind of analysis summarized in a single table. That's up to the requirement. That's up to the person who is trying to do it. Okay. So that is with respect to the definition of your analysis. So this is an example of a XYZ project. These are the cases which are being defined. So you have different components of different points in which, or different parameters of analysis. Amplifier is an analysis element or a case. DC gain is a particular case. Bandwidth, actuator, response time. These are the different things or different points or parameters or certain technical terms on which we are doing the analysis. We analyze yes, amplifier, we analyze the DC gain, we analyze the bandwidth, we analyze the actuator, we analyze the response time. So you have the units, specification, actual, status. So you have a specification value, you have an actual value which gives you the minimum and maximum and average values. Then you tell it's okay, which alert scenario, or it can be something which can be skipped. So this is the example of an analysis table. So that we will see. I mean, we will see an analysis table example when we finish the explanation of this thing, so that you get a clearer picture of what this analysis is. And the whole point of the online classes and other things is to we will give you a briefing of what you are trying to study. Then you study it by yourself. Come back with the questions. That will be the ideal method in which the online classes can be effective. Okay? That is the same approach that I'm going to follow. I will explain the analysis table. You can go through the example scenario given in the textbook. Come back with questions, and I want questions from your part so that things can be understood in a much better way. So moving along. So that's about analysis table. The rating factors. When you have a rated value, uh, there might be conditions where the rating goes off. Say after some amount of 10 years, whatever has been rated will not be given out. So accordingly, you'll have to calculate the value. So that's called as de-rating factors. You are given a particular rate, but say you expect an error of 0.01, but after 10 years, that might be increased to 0.02 when you consider a measuring equipment. So this is called as derating factor. The rated values are derated according to the conditions in which you are going to do the analysis. So to help the account for uncertainties in the design, stress is where derating comes into factor. It's usually 10% may be applied to the datasheet limit. So according to the datasheet limit, you another add or subtract your 10% value when you do your stress analysis. Okay. Then worst case maximum stress applied to the part should not exceed 90% of its actual limit. Rewriting factor will get there. So it's basically something which is associated with the applications. There are certain applications where derating factors need not be considered, but there are applications where derating has to be considered depending upon the criticality of that particular application. So for example, capacitor, which a aluminum type of capacitor. The parameter is RMS root mean square, which is given in amps or your current value. re-rating factor can be 0.80. That is determined by lots of things. What the criticality of the thing is, what is your age limit associated with it. According to that, you apply a de-rating factor, RMS amplitude value. According the rated value, 0.80 of the rated value can be considered for analyzing stuff. That's all about de-rating. So this is an example. Diode forward amplitude 0.90. These are the certain example scenarios where you apply your de-rating factors. Okay. Vary depending upon the application. With non-critical applications having little or no re-rating, while critical applications, so almost, I mean, critical application you apply much re-rating, whereas in non-critical it's not required. Longer operating lifetimes by reducing wear out stresses, particularly for mechanical assemblies. Some parts this is not required because it's not going to be used for the lifetime of the product. Uh, the re-rating factors will, I mean, if there is no uncertainties, there is no requirement of what is it, huge real-time requirements and all. This is just a this is just a what is it? This is just a over the above and over and above analysis. So that basically means it will lead to our design and associated higher cost. And now you tell that you are going to derate something, automatically it will have to function according to the derating factor. Automatically it means that you have to make a change in the design, which will lead to an over design if it is not required, and automatically it will have cost implications. So you use derating factors only when it is required. Okay. So that's the idea. So employment of WCA plus risk assessment methodology will significantly allowing the use of derating factors to be reduced or eliminated in many cases. Okay, so you can understand from WCA plus whether this is what is it? This is something which is required or not. Okay, that is up to the designer to decide. WCA gives you a risk analysis statement of which will help in you in analyzing the risk factors, and then you can accordingly make the corresponding changes. Okay. So that's the whole idea of WC plus. Now, then the first was your what is the jurisdiction of the analysis. Second was derating factors, identifying the derating factors. Third, determine the global parameters. The global parameters which are associated with your design: temperature, pressure, aging limits, power source limits. These are the common global parameters which are associated with the functionality of your design, which has to be considered when you do your worst case analysis. Okay. So defining global parameter at the start of the analysis ensures the separate sections of the analysis will employ a uniform baseline. So you initially itself tell that these are the parameters on which you are going to limits or source limits. These are the parameters on which we are going to do our WCA analysis. So we are going to make the design analysis based on these parameters, these kind of global parameters, based on the environment in which it is working. For example, if you are working in a very cold environment, you have to consider the cold scenario. If you are working in a hot environment, you have to consider the hot scenario. Whatever. So you will have to decide on what those environmental factors which will be used as part of your analysis. Okay. So that is your determining of your global parameters. For example, in this particular case, the global parameters which are considered are temperature, voltage, power supply voltage of 5 volt, 12 volt, and then your aging factor, aging tolerance factor, 1000 ppm, parts per million. So TO lag is something which is considered it as a minimum maximum. So these are the global parameters which are considered for whole design. For any particular analysis, we will be considering these global parameters. The changes in these global parameters, the equations related to these global parameters will be considered when you do your analysis. So ambient temperature, supply voltages, and agent tolerances are the common global parameters which are considered. Now, the fourth and the most important one is to develop the design equations. As I told you, this is completely related to something associated with what to say. Uh, Associated with maths. So maths is all about equations. So you need to familiarize with the equations which are associated with it, from which to identify these kind of minimum and maximum values. So you use your textbooks, math-based softwares, application literature, everything that you can see all across your particular agendas can be used for identifying these kind of design equations. So it's just telling about those particular kinds of stuff which you can go through by yourself. Relevant documents. tolerances are very difficult to find. Aging factors are very difficult to find because it is determined by lots of what is it non-fixed equations, which makes it's very difficult to find out a real equation which associate maths which is associated with it, because aging is something which is we cannot define aging with a certain set of parameters. Even for human, you consider the human case also, people age differently, so considering a mathematical equation for aging is quite difficult. So these are certain issues that you face when you develop design equations. And from this is where you go on to the major thing, that is to identify your worst case solution. So the idea is to identify the worst case as solution associated with the parameters, with the what is it analysis framework that you have found out. Your whole idea is to identify these worst case solutions. You form a mathematical equations, apply the values to these equations, and find out what are those minimum maximum values which can happen in a worst case scenario. Okay. So it's purely maths here. So you have monotonicity, which is basically something which is associated with telling that a variable with respect to a parameter, if it follows a graph which has only one minimum and maximum, fine and good. Just need to identify if x is a variable which takes values from 1 to 5, you can get the minimum of an equation which has x with a x variable, I mean, x equal to 1, and maximum you can get from x is equal to 5. That's the idea of monotonicity. It is a mathematical term. It is very relevant when you try to identify your minimum and maximum values. Okay. Variables which will cause the equations to have minimum and maximum values. So the idea is to values of equation variables which will give you the minimum and maximum limits. You have an equation called as y is equal to x squared plus 2xy plus y squared. You want to identify z is equal to x squared plus 2x squared plus y squared. Now you want to identify the minimum value of z. Z is equal to x squared plus 2xy plus y squared. You want to identify the minimum and maximum value of z. That is what is required for your analysis. Now you know the variables associated are x and y, and x has this particular range, y has this particular range. By substituting the values of x and y, when will you get the value of z with a minimum value? That might not be directly related to the minimum and maximum values of x and y. That's the whole point. So you need to identify it with respect to a variable v. So an equation is monotonic with respect to a given variable v if there are no peaks or valleys in equation solutions, as the variable is varied from its maximum and minimum. So you have a direct line graph. Variable is v, given variable is v, you have an equation, say x is what is you are trying to identify, the variable is v, you vary vm v from vm minimum to v max, vm to vx. And if there is no valleys and peaks, you have a particular point where you will get the maximum value and a particular point which will get the minimum value. It will be associated with v minimum and v maximum. Okay. Mathematically, if the derivative of an equation with respect to a given variable is not equal to 0 or variable range of values, then equation is monotonic with respect to the variable. Derivative slope of an equation with respect to a given variable, derivative, partial derivative with respect to a given variable is not equal to 0. That means it has to have a non-zero value over the variable range of values. Then the equation is monotonic with respect to the variable. So this is the mathematical definition. This is the way in which you identify your solutions to your equations. So minimum maximum. This is an example of monotonic equation. So there are no high. This is a direct. This is your v variable. This is x is what you are trying to identify. We get the minimum value of x from the minimum value of v. It follows that the minimum and maximum values of the equation with respect to the end values of the variable. Your minimum and maximum. So for here example, x, if you consider it having a usual x and y axis, v is the variable, is varied from vm to vx, vm meaning the minimum variable, vx meaning the maximum variable. So x value also take the minimum at vm, maximum at vx. That's here. Vm vx is the variable. X take the maximum value at Vm, minimum value at Vx, but the points remain the same. We get the minimum and maximums at Vm and Vx. There might be changes because if the equation is 1 by x, inverse value, so Vm might give you the maximum value of x, VH must give you the minimum value. That's okay, but points are fixed. You get these minimums of x from the minimums of the variable v. That's the whole idea of monotonic equations. Is it clear? Do I require something more? Are you completely left or what? Just to get a feedback from your part? If everything is fine, can I proceed? Or have you all set? Okay, I will just continue with my discussions, and I think I will be able to stop within 5 or 10 minutes. So this is maths. This is the maths that you have studied in your engineering. This is the maths that you have studied in your plus twos and all with differentiations and all. So this is the idea here. So the whole idea is to calculate. We are not going for an exact solution. What we require is the minimum maximum associated with a particular expression with the variables getting the variables coming into picture. So this is monotonic. This is non-monotonic. As you can see, x is the variable that we are trying to, x is the value that we are trying to identify. Vm is the variable that we are considering. When the Vm is varied from the minimum value to the maximum value, from a value of Vm to Vh, this is going a dip. So Vm is the minimum value of V, Vh is the maximum value of V, but x has a completely different point of minimum. Maximum is okay, but the minimum here is at a very different point. So this basically means this is a non-monotonic solution, which requires further analysis, which requires some mathematical tools to be used as part of your particular analysis. Again, another example. Again, here your V is taking values from Vm to Vh, Vm being the minimum value, Vh being the maximum value, and X will move along, and Vm gives the minimum value of x, but maximum value of x is not given by Vh value, but is given by a completely different value, because you have a peak here. In this particular case, you have a value here. So this is an example of a non-monotonic equation. The other one is a monotonic equation, very easy to deal with, but non-monotonic equations are very difficult to deal with. So that's idea. So evaluating monotonic and non-monotonic equations with non-monotonically related variables should be evaluated at all zero slope points. So that's the important point. So to get the maximum value or the minimum value, you can go for your zero zero slope points, or points where the differential equation value is equal to zero with respect to that particular variable. That might be giving you the maximum value. So if you have a particular point in your variable where your particular expression becomes zero, that can be the minimum or maximum value. Super. Variables should be evaluated minimum and maximum of all variables. Okay. Even if x contains peaks or values with regard to v, this does not mean that minimum maximum solutions of all peaks or values, because infections may occur. That basically means, see, in the other two cases, we found out that this is a single value, and you are having the maximum minimum value of x at this particular value. So the slope is equal. It is having a minimum value at the differential point when it is equal to zero, and here also it goes the same. But when it comes to such kind of a scenario where you are having x vm vh, you are having a fluctuating value, so you have a peak and a value. So where is the minimum value of x? It is in the value. So you have choices of it, you have different options of it. Even if x contains peaks or values with regard to v, this does not mean that minimum maximum solution of occur at the peaks of values, because infections may occur. So this it might not happen that it might be in the minimum maximum values. It might be in a completely different value. So here there is a minimum and a maximum, but your VM, that's value is getting the minimum value at VM, and that's value is getting the maximum value at VX, even though you are having a what is it, peaks and values. Okay, so even if x contains peaks or values with respect to regard to v, this does not mean that the minimum maximum solution of x will occur at the peaks of value, because in fact inflections may occur. That is an example is being shown here. So all these things are possible. How do you identify your worst case solutions by inspection. There are simple examples. This is a worst case solution by inspection. You're not going for any huge amount of maths. You just look into it. X is equal to A by B, A is equal to 1 to 3, B is equal to 2 to 4. Okay, so A is equal to A by B is the equation. A is a variable, B is a variable. A takes the values from 1 to 3, B takes the values 2 for 4. What we need to identify is minimum and maximum of X. How do you do it? By analysis, we know that the minimum of x will be a having the minimum value, b having the maximum value. That is something which logically we understand from the study of mathematics. So the minimum value of x will be 1 by 4, and the maximum value will be a max by b minimum. That is, x max is equal to 3 by 2. This is something which you know by inspection. So you automatically can know that and can understand that your minimum value of x will be 1 by 4 and the maximum value of x will be 3 by 2. This is something which is implied. There's one way of identifying your worst case solutions, very simple inspection method, but this is a very simple equation. That is why, and very few number of variables, that is why we were able to associate those worst case solutions with respect to x in a simple manner. And moving along, we can do it by differentiation as well. So you uh, differentiate using this prior example. The derivative of x with respect to a is taken. It's 1 by p, or 1 by b is not equal to 0 for any value of b. Therefore, x is monotonic over the range of a. So how do you conclude it? You differentiate your equation with respect to the variable. So with respect to a, you differentiate your x. So a by b is differentiate with respect to a, which gives you 1 by b. With the range b is equal to 2 by 4, there are no points where your x value is going into 0, which basically means you are having a monotonic equation. So you can easily identify the minimum and maximum values. Okay. So which means that the minimum or maximum value will correspond to the minimum or maximum value of x. Likewise, x is monotonic with respect to b as well. Dx by db will be minus a by b square. Differentiation, big thing, something which you have studied in your +2 and engineering, something which will not be understood easily by most of the people. But here it's a very simple case. So you just differentiate your x with respect to b. It gives you a solution of minus a by b squared. Give the values of you give all the values of a and b minimum and maximum. You never get an answer equal to what is it, 0. At this point, the analyst knows that minimum and maximum is a and b will yield the minimum and maximum is x, but does not know which combination of a and b are required. That is, 4 calculations are required. So, from this analysis, even though by inspection we have done the analysis, when you go, this is a simple case. This is to make things clear. So when you do differentiation, you differentiate your particular expression with respect to the variables a and b. See if you are getting your what is a values non equal to 0. If there is a 0 possibility coming for this particular scenario, you will understand that this is not monotonic. We need some other kind of method. Here we understand that both these are monotonic. Now we don't know which is a combination, which minimum maximum gives you the maximum minimum result. So you go for all possible calculations, 4 calculations: a minimum by b minimum, a max by b minimum, a minimum by b max, and the other possible combinations. From that, you identify which is the minimum value and which is the maximum value. So we have 4 variables. We know that the combination of these things will be the one which will be used. So a minimum by b minimum, then a max by b minimum, then a minimum by b max, then finally a max by b. From the above, we know that x minimum 1 by 4 and x max is 3 by 2. So it is the same as that. Now that was a simple case. Now we move on to next level of analysis. So consider an expression which is equal to x is equal to 3 sine omega t. Omega t is your radiance, which is given, which ranges from 0.6. You need to understand that you are trying to analyze the minimum and maximum solution of an expression, and you know the variable range. Only by knowing the variable range, you are trying to find the solution. So x is equal to 3 sine omega t. Omega t is equal to 0.67 plus 2.56 radians. The derivation of x with respect to wt is 3 cos omega t. Setting the derivative to 0 and solving for wt. Okay, so you get, so this is an example where you have a monotonic solution. So there is a possibility of the value being equal to 0. So you get that from one point. Therefore, a minimum or a maximum value of x will occur at wt is equal to pi by 2, which is within the range of, so your solution of 0 is within the range of 0.67. possible solution of x are, so you give the minimum value, that is 3 sine 0.67, then 3 sine 2.56, then you give the value of pi by 2 1.7, so using zero slope value of the variability. From the above, the worst case results are your minimum value is 1.64, the maximum value is 3. So just go through it, go through this particular problem, and just tell me if you have any doubts. I'll stop here. I mean, I'll proceed after a few minutes. But currently stopping here. Just tell me if you have any doubts with respect to this particular example that has been considered. It's a very simple example, but to be clear that you are understanding things, I want to get a feedback from your part. It's fine. We will proceed. This time I'm not forcing you to ask questions, but the next time I will do it automatically force you into questions. So there are people who have left. It's okay. Might be issues related to. So are there any questions from your part? Somebody who hasn't understood can give the response either through audio or through chat or through, I don't know. Define. No questions. Are you able to hear me? Moral has left with their mics. 5. Okay. Typo error. Hmm. 3 had their mics in their ears. And Maria has given the opinion and left. I guess most of you are fine, and if there is any issues, you can always interrupt me while I'm taking class. That's fine. Okay, so we will continue with our presentation. So that was okay. So the idea is you use your mathematical skill set to identify the minimum and maximum value. You either directly get the minimum and maximum values, or you use your differential equations to find out your minimum and maximum value. So that is what what's being done. So simple inspection differentiation was used to calculate these kind of values. Another method is to use brute force. Just give these particular values to each of these particular variables and then identify which is the minimum value. All equation corresponding to the range of values of all data identified in minimum value. Only necessary to use the minimum and maximum values so we can calculate it. If non-monotonic, if monotonic, minimum and maximum is fine. If non-monotonic, there must be enough sample points for variables to ensure that peaks and values in equation solution will be identified. So as you can see, there are different peaks and values which can come up. There might not be a single solution, there might be more than one solution. So you need some variables to be used or some samples to be given so that you are sure that these are the minimum maximum. Monotonic not required. You can directly take the minimum maximum. So here is an example, non-inverting voltage feedback amplifier gain. So that is what we are trying to analyze. This example is desired to determine the gain of the amplifier from the analysis table section 2.1. Analysis table section 2.1. Okay. So a gain of 185 to 215 is required, and you have 200 plus or minus 7.5%. So that is what the gain is. 185 to 215 is required. Now DC gain. So here is a particular scenario. DC gain is a case that we are considering. It has a minimum and maximum value of 185 and 285. What is my actual minimum and maximum and average values? So we're not going to the status part. It's checking into what is the minimum and maximum values. 1.1 requires a closed loop gain of 185 minimum to 50 maximum volts. Calculations are to be recorded in the worksheet. Worksheet may be a form of a spreadsheet or a generated. DC gain size ADC, which is the left uh, hand side of the equation of the unknown, right hand of the equation, defined by a standard equation for non-inverting amplifier. What is the standard equation for your non-inverting amplifier? Okay, this is quite interesting. Uh, do you have these slides with you? Okay. So you can go through the slides and try to understand what they are trying to do as part of this particular analysis. So this is something which you have to do by yourself and come back to me with the questions. I will just brief you through the scope. The first one, you have your DC gain. Then you have the different variables which are of consideration. ADC, DC gain, A0 is an open loop gain, B is your feedback ratio, A0 open loop gain has an expression like this, B is again part of, so you start with ADC. ADC has an expression given by A0 by 1 plus A0 into B. Now we need to know A0 and B. Now move on to A0. A0 is open loop gain, B is the feedback ratio. A0 moving to A0, the expression is 1000 into 1 plus TCA into TU. TCA is your temperature, ambient temperature, and the other two temperatures which are associated with your particular uh, system. Then B is a feedback ratio given by R1 by R1 plus R2. Now you need to know TCA, TA, R1, R2. Now going back to R1 is given by inverting input resistor. Uh, TI R1 into 1 plus TCR R1, TA minus 225. R2 is feedback resistor, again given by an expression like this. Independent variables TCA, TA, one second. Independent variables TCA, we identified that the variables which are used, which are required for checking the minimum and maximum value of ADC gain are TCA, TCA, then TA, TA from this TA from here, TIR1, TIR1 from here, TCR1, TCR1 from here, TIR2 from here, TCR2 from here. So this has to be not that even though R2's tolerance are the same value as R1's tolerance, they must be separately calculated. Whatever. So these are this is the point. So you start from an expression, you identify the variables, we identify the dependencies of these variables, move again to the expressions and see which are the variables which are going to influence your ADC. So this is an example scenario. So moving on to the next slide. Okay, so this is a brute force example. So TCA has a has a minimum value of this, maximum value of this. TA has a minimum this, maximum value of this. TI, everything has a minimum and maximum associated with it. Okay. Okay, so this the points and rate defines the number of sampling points of the range. In this example, someone has experience with the standard equations and knows it to be monotonic throughout. Okay. So since these expressions are considered to be monotonic, we are considering only 2 points. Only the minimum maximum values each minimum are used during computations. So we are taking only 2 points. That is because we know that these variables are monotonic with respect to the uh, ADC gain. So this is something which has been analyzed and we know that. Under that assumption, we are taking only 2 points. Non-monotonic with respect to the equation or its monotony or unknown, sampling points of the variable would need to be increased sufficiently to resolve any peaks or values in the range. After setting up the worksheet as described above, a calculation table is created with a calculation required for each combination of variables. That is n is equal to V1 samples into V2 samples into Vn samples. And total number of required calculations, Vn, the number of sample points for the nth variable. So in the above example, considering all these scenarios, the number of calculations which are required 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That is 2 into 2 into 2 into 2 into 2. That is 2 into 2 raised to 6. It's equal to 64 calculations. For each combination of variables, solution to the primary expressions is calculated. Note that is an important data. So you do the calculations for each of these particular set of variables. So the minimum and maximum values of one is considered. Find the solution after observing the supporting equation, the primary equation state. So considering all these quantities, the expression of ADC looks like this. Now, using this particular expression, we are going to calculate these particular values. 64 equations are required, and from that particular set of equations, we are identifying the minimum and maximum values. So what I want you to do is go to the textbook, identify the problem, understand it, write it on a paper, and see how it works. Just make sure that you submit this particular paper with the corresponding values neatly defined by the next class. That is, the next class is on Monday, so you can do it during your Saturday Sunday breaks. You got the idea. So this is the way in which you do your brute force analysis. Uh, this is an example scenario. You go back to the equations, identify the things, and find out how they have done it. So that's about how to calculate your minimum and maximum values. Now, 2 points, 2 works which are assigned to you. One is to calculate your this particular example scenario, write it down in a paper and show it to me or submit to me as a PDF when you come and when you attend the class on Monday. You need to submit your assignments on Friday. It was a very delayed break that I've given you. Assignments, by assignments, I mean uh, the written assignment part and the presentation slide part by both of you. And your presentations will happen. I will assign the presentations next week. I will tell you the dates when you need to present and all. Next week, I will tell you the dates on Monday or next week sometime. So you need not present it on Friday. Presentations can happen later. I want the prepared slides on Friday. So 3 things that are to be submitted on Friday. One is your written document of notes of whatever you're trying to. You need to refer the textbook and internet or other sources. Also write the reference in your particular essays. Then try to find questions from that particular topic. I have already given certain question papers. You can use that as well as your own analysis of the frame questions. That is an assignment to one person among you. So it should have a minimum of say 5 to 10 questions. You cannot just write what is this, this is what you we are. I'm expecting you to write uh, questions for 5 mark and 10 marks. That is how your university question paper will look like. 5 questions of 5 marks and 10 marks on the topics which have been assigned to you, which will be submitted on Friday. Prepare a particular presentation, submit it along with this. So you can either divide your presentations into two and submit or combine it. That is fine with me. I will take it as a group work, but both of you have to present some part of it. Then these 3 things are to be presentations. I don't want the audio presentation part currently. Keep it as such. Currently, I'm looking only into the slides. Presentation, we will be doing it live through these particular classes. Next week, I will give you the dates and then you can present those particular parts. Clear? If you have any doubts with respect to this, you can get back to me. So I'm stopping my class now. I'm stopping my presentation. So you have work for you in the next class for the next week to do the works accordingly. So there are certain students who have left and come out. So I will pass on the video link of my class so that you can go through it and understand the stuff. If you have any doubts with respect to whatever I have told now, you can ask now. If there are no doubts, you can tell thank you and go off. But I will make you ask questions once I complete this particular portion. That's for sure. Okay, thank you. I'm stopping my recording. 1 second.